Okay, so now I'm going to show the CAD program that we use to design the OHMMM robot. It's called Alibre Design. A-L-I-B-R-E. Starting up here. This is the 2012 release. Personal edition, Alibre PE. And I'll load the whole assembly of the entire robot. It takes a minute or two to load. This is running under VMware, Windows 7 and VMware on my Mac, running OS 10. And so this is loading a model of the entire robot. The base, the arm, the electronic stack, and the mast. And that model is structured as a hierarchy of sub-assemblies. And at the bottom level of that hierarchy are parts. A part is an individual solid object. So we decided to use Alibre because it's reasonably priced and accessible, and is definitely sufficiently powerful to design all of the parts for OHMMM. There are three kinds of mechanical objects in OHMMM. So there are off-the-shelf objects like the drive motors and the arm servos and the circuit boards. There are laser cut parts, which are the translucent blue flat plastic pieces, and there are 3D printed parts, which we've been printing for real in white, but in the CAD model are actually shown in red here. So this is the full model of the robot. Try to zoom in a little bit. And so again, the blue pieces are of course the the laser cut parts. The red pieces are what we do on the 3D printer. We make those out of ABS plastic. They actually print out white. And the remaining things are off-the-shelf components. There, for example, is a representation of the battery, the rear Omni wheel, etc. And so my task here today, I'm not going to actually modify the design, but this would be the right place to do that. I'm going to just prepare some files for the 3D printer. So in particular, I want to print a new copy of this part, and this part, and this part, which are the left and right rear wheel brackets. So I'm going to open those in separate windows. So you edit in separate window. That's the left rear wheel bracket. And I'll go back to the original window. And I'm going to also edit this in a separate window. And so what I have to do for each of these parts is I have to save them in a format called STL, which originally stood for stereolithography, which was a different form of 3D printing. So here, for example, is the right rear wheel bracket, and I'm going to just export this. So let's see, export. I have it set to STL by default. I'm just going to save it on my desktop. Let's see. And actually, we've already, so when we provide all the CAD files, we also provide the STL files, which correspond to the CAD files as we have designed them. You would only need to re-export if you change the design of any of the parts. This is the left bracket. Export that as well to the desktop. Save that. minimize that program, and now actually, so here are my two files. Windows detects them as some other file type, but those are the files. What does it think they are? Certificate of trust. We'll now fire up the Catalyst program, which is the processing software for our 3D printer, which is a Dimension printer. Dimension's a subsidiary of the company Stratasys that makes what are called FDM, fused deposition modeling 3D printers. So this is the processing software for our Dimension printer. The model is uprint 3D, and I'll open those STLs, do one at a time. Start with the left. So open that. One problem with STL format is that it doesn't embed the units, which are typically either millimeters or inches, and so the processing software has to infer whether the CAD program saved in millimeters or inches. And here it's saying that if it interprets as millimeters, it comes out very small. So in fact, it should be inches. So I'm going to let that be inches, and now that's correct. It infers an orientation for the part. It's going to build the part from the bottom up, and right now it's got that part down, which is good. I will let it build that way. There are different considerations for the build orientation in terms of the strength of the part, the accuracy of the geometry, and how much support material is generated for overhangs. There are two types of material, the build material and the support material. So that's going to be okay. I'm going to change the interior to solid so that it will actually fill the whole part rather than make some voids in the interior, which saves material but also makes a slightly weaker part. And that's that. The orientation is good. I have to go back here, I think, and then I have to say add to pack. And you can see that the software is slicing the part in horizontal layers, planning the extrusion of the support material, which is shown now in purple, and it has added this as an outline to the pack here. Now I'll go back and I'll open up the right bracket, do the same thing. See, here it's inferred another orientation, which is not the way I want to build that part, so I'm going to change that. The orientation frame, and one way we can do it is, let's see, orient selected surface, make that the bottom. There we go. So now that's going to be the bottom. And then I will do add to pack. And it's placed it in the pack here. And this is a top-down view of the build surface of our particular 3D printer. And so now I can position these in, where I want them to be on the build surface. And so I'm just going to put them in the back here. And I will say print, and of course this has been set up to talk over the network to our printer, which is turned on right now and waiting for a part, and I've sent it to the printer, and if I check the printer status, there it is. This is the print queue on the printer, and it's waiting for me to go and start the build there.